We're going to take a look at in the inner ear is going to be equilibrium. We have both static and dynamic equilibrium. Static equilibrium is really looking at when the body is steady, and it's really this kind of head position, also kind of linear acceleration, so that getting pushed forward by a vehicle type of thing. So that is going to be monitored by the utricle and the saccule. The other one is going to be the dynamic equilibrium, which is rotational movements of the head and really the body, and that is going to be with those semicircular canals. So again, linear acceleration is kind of being moved forward by like an acceleration. Angular acceleration is going to be those semicircular canals, which again is going to be any type of rotational movements, like it says, of the head. But I mean, unless you're just kind of doing something like this, if the head spins, the body has to go with it, otherwise it doesn't work that well. So within the sagittal and utricle for the linear acceleration, like the tilting and head position, it's going to be the actual organ called the macula that is going to be in charge of really monitoring this. And what you're going to have is you're going to have these little cilia that are standing up, and then you have a specialized one on the end called the kinocilium, and it's these hair cells either bending towards or away from this kinocilium that are going to determine does impulses speed up or slow down, and that's going to tell you, is your head leaning forward, is your head leaning backwards, is it leaning to this side, is it leaning to this side. What is sitting on top of all these these cilia are going to be what is called this otolithic membrane. So it is this kind of gelatin, and then it has these small little calcium rocks, so pretty much, or crystals, called otoliths. These otoliths add weight to that gel, and it's really the movement of these stereo and kinocilium either towards or away from that kinocilium, that is going to determine which way your brain perceives your head as being tilted. So when your head is upright, you're getting equal pressure on there. There is this minimal stimulation. You're going to get this kind of standard frequency of impulses being sent back to the brain. When you tilt your head and those stereocilia move towards that kinocilium, it's going to lead to a depolarization of these hair cells and an increased nerve frequency. If your head tilts in the opposite direction, it's actually going to move those further apart, and you're going to get a decreasing frequency and hyperpolarization of these cells, and your brain interprets that as your head being tilted in the opposite direction. So, and this is taking place, like I said, in that utricle and the saccule here. One is kind of tilting this way and this way, the other one is this direction. But again, this is showing you that kinocilium, that specialized one in the stereocilia with the otolithic membrane, with the otoliths in there increasing the weight. When you get just upright head position, you have this standard frequency. If you start tilting your head backwards, these the stereocilia are moving towards the kinocilium. It increases that firing rate. If you tilt your head the opposite direction, it inhibits that firing rate to a lesser degree than kind of the standard firing rate. So that's how your brain would know which position your head is tilted in. The other thing we're going to be looking at here is the semicircular canals and the ampulla, which is the main where the receptors are for this type of this type of equilibrium, So within that area, you have this crystal ampullaris, which again, we're going to have these cells with the kinocilium and the stereocilia, again, in this little gelatinous, in this case, it looks more like a mushroom top, but you have kinocilia and stereocilia embedded in there. So it's something like this, and depending on if this gelatinous mushroom top is moved towards or away, again, we'll increase that firing pattern one way or the other. Again, we have one in both ears, so when you're spinning in one direction, you're going to increase firing patterning on one side, decrease on the other, and that is going to say, okay, we're spinning this particular direction. So rotational head movements, you have that endolymph that's traveling through there. It is this fluid inertia that is going to bend that little gelatinous top and move those stereocilia towards that kinocilium. And again, if we lean it towards the kinocilium, you're going to increase frequency and can respond to changes in the velocity of this fluid traveling through those ducts. So again, when that fluid travels through there, you can see it's going to bend these towards that kinocilium, and that would increase that firing pattern and say, okay, we're rotating in this particular direction. If you were to rotate in the opposite direction, again, you're going to get stimulation on one side inhibition on the other, and that's going to say which way you're rotating there, because again, we have semicircular canals on both sides of the head. And again, you have them in each direction, so one here, so this particular loop, it would be if you're just spinning rotationally like this. If you had your head down, that would be this loop, and if you had your head to the side, it would be this other loop right here. So you're getting those X, Y, and Z planes with these different semicircular canals. A lot of times people can get what is known as motion sickness, and a lot of times this is when you're getting this really disconnecting signals. Your visual activity is kind of saying that you're not having movement, where your vestibular senses are giving you a conflicting signal of movement. It's kind of like saying we're moving, no we're not, and then your stomach just kind of says, well, I'm going to vomit just in case. One of the ways we treat this is with Dramamine, which is going to decrease brain activity a little bit overall. It makes you very drowsy, but it actually decreases that vestibular senses a little bit, which leads to a little bit less of that disconnect and can help with the motion sickness. So those are your vestibular senses. The last couple of shows here we're going to take a look at are going to be with the visual senses, looking at overall anatomy of it first, and then going through some of the physiology of how we go about detecting light. So we will do that next time.